Okay, so we're going to get into the bulk of the presentation here. We're going to do a comparison for a 250 megawatt data center, and we're going to compare three different technologies. The case study would be for a hypothetical 250 megawatt data center that has no grid connect, so it's an islanded system. It needs power within 2 years. It requires an uptime and power availability of 99.9% reliability. Industry calls this 3 nines. The power price is economic at $90 or 9 cents. So US, and the equipment is based on new equipment. We're going to compare the reliability of such systems. We're going to compare the ramp rate resiliency, the lead time and deployment, economic viability, and we're going to touch on space requirements. And the three technologies that we're going to compare against each other are a generic 50 megawatt simple cycle turbine, a generic medium speed 20 megawatt engine, and our 20 B4000 2.5 megawatt unit. So a couple different things that I want to just highlight in terms of inputs to our model. So while different turbines are capable of handling different load steps, for the model, what we've done here is we've limited the minimum that a generator can run. Actually, we've set it lower than this in our model, but typically turbines like to be loaded much higher than this because of fuel efficiency. Medium speed engines and high speed engines can run lower than this, but again, in the model, we've limited it to 50%. And this allows us to ensure that we're staying within the fuel range that are posted for these data sheets. One thing you'll know right off the bat is that as turbines, as the load factor or turn down rate is reduced, you'll see that the fuel consumption per megawatt dramatically increases on turbines, whereas on engines, you see that there's a relative increase in fuel consumption, but not as dramatic as turbines. And you'll see that in some of the calculations we show. I want to talk about load step capability. While all three of these engines are capable of handling probably higher load steps, we've limited in the model our design to 10% for continuous operation, 15 and 20%, because though we can ramp fast, all three of these units typically like to run at as close to full 100% loaded and consistently at that. And you'll see why this is important later on. Finally, electrical efficiency. Simple cycle turbines can achieve at a lower heating value at fully loaded up to 40%, medium speed up to 50. And I want to highlight two different configurations for our Rolls-Royce engines, which is at 1 gram per brake horsepower, which is 500 milligrams per nominalized cubic meter, NOx, should have that there in NOx. We can produce 43.6% electrical efficiency. And if we go up to 800 milligrams, we can get up to 44.1%. And these are at 60 hertz.